BenchIE FL, a manually re-annotated fact-based open information extraction benchmark. This paper introduces BenchIE FL, a new open information extraction (OI) benchmark designed to improve upon the existing BenchIE. BenchIE FL aims to provide a more accurate and reliable evaluation of OI systems by correcting errors, inconsistencies, and limitations in the annotation and matching functions of BenchIE. The authors also present a comprehensive review of previous OI systems and benchmarks, highlighting their strengths and weaknesses. The paper begins with an overview of the development of OI systems, from rule-based models such as Reverb, Clause-IE, and Mini, to neural models like Emo-JIE, M2OIE, OpenIE6, and Compact-IE. These systems are trained on bootstrapped data from earlier extractors, with varying degrees of success. The authors then discuss the creation of OI benchmarks, including OIE 2016, Wire57, CARB, and BenchIE. Each of these benchmarks has its own set of annotation principles, text corpora, and matching functions, leading to varying conclusions about the best performing extractors. The paper highlights the limitations of BenchIE, such as missing facts, incorrect annotations, and inconsistencies in the matching function, which can lead to biased results. To address these issues, the authors propose BenchIE FL, a re-annotated version of BenchIE. BenchIE FL uses new guidelines for sentence annotation and tuple matching, resulting in more concise, precise, and pertinent annotations. The new benchmark also includes a more flexible matching function that captures more valid extractions, providing a fairer ranking of evaluated systems. In addition, the authors compare 7 OI extractors and demonstrate that believed state-of-the-art systems are not necessarily the best when evaluated on BenchIE FL. They also show that the scores of extractors on BenchIE FL exhibit a much stronger correlation with their performance on 3 downstream tasks. Here is a combined summary of the 2 pages, covering all major points and highlighting novel ideas, significant findings, and important arguments presented. Error types in open information extraction, OI, annotations are categorized into 5 types: missing fact, false fact, irrelevant fact, double annotation, and double meaning. These errors are prevalent in existing OI benchmarks, such as BenchIE, and necessitate more thorough annotation guidelines. The authors annotated facts output by various OI systems and found many cases where a system made a valid extraction that did not match an annotated fact. This led to the development of a new matching function to capture more matches between extracted and annotated tuples. The authors propose annotation guidelines for OI output, including principles such as informativity, minimality, exhaustivity, relation completeness, and inference. These principles aim to ensure that annotated facts are informative, minimal, exhaustive, and relationally complete, and that inferred tuples are included when implied by the sentence. The guidelines are motivated by the need for solid principles in OI annotation, which are often lacking in existing benchmarks. Examples illustrating these principles are provided, showcasing how they should be applied in annotation. The authors argue that existing benchmarks, such as BenchIE, do not adequately capture these principles, leading to errors and inconsistencies in annotation. The proposed guidelines aim to provide a more comprehensive and accurate approach to OI annotation, which is essential for downstream tasks such as question answering in knowledge-based population. Furthermore, the authors discuss the need for matching guidelines to determine which extracted tuples should match with which annotated clusters. They propose principles to guide this process, including the need for exact matches and nuances such as allowing for optional words and capturing implied information. Examples of these principles are provided, and the author's full matching guidelines can be found in an appendix. In the research paper, the authors introduce BenchIE FL, a re-annotated version of the BenchIE corpus, focusing on improving the annotation guidelines to enhance the quality and specificity of open information extraction, OI, benchmarks. The new guidelines emphasize relation specificity, word choice, and level of detail, aiming to ensure that annotated facts are precise and comprehensive. A validation experiment was conducted by 2 annotators, who found that BenchIE FL annotations more closely follow the guidelines, with fewer errors in terms of exhaustivity, minimality, and incomplete relations compared to BenchIE. The authors also developed a new matching function for evaluating OI systems, which captures more matches than the exact matching used in BenchIE. This function includes three types of heuristics: alternative formulations, AF, level of detail matching, LOD, and punctuation, punc. These heuristics are designed to address issues related to word choice, level of detail, and punctuation in the annotations. The F1 score of the matching function variance on BenchIE FL shows that the exact match function is outperformed by the new heuristics, indicating a better alignment with the guidelines. The authors present a comprehensive evaluation of open information extraction (OI) systems, focusing on the development of a novel benchmark, BenchIE FL, and its accompanying annotation toolkit. The authors demonstrate the effectiveness of their approach by comparing various OI systems on downstream tasks, showcasing the superiority of BenchIE FL in reflecting real-world performance. The authors begin by describing their annotation guidelines and the creation of matching annotations, which enable the evaluation of OI systems based on their ability to extract relevant information. They propose an exact matching function, which is shown to outperform other scoring functions in correlating with manual annotations. The authors then evaluate 7 OI extractors on 3 downstream tasks: assertion-based question answering, complex questions answering with quasi-knowledge graphs, and knowledge-based population. The results demonstrate that BenchIE FL's rankings closely follow the rankings obtained by evaluating OI extractions in these downstream tasks, highlighting its effectiveness as a benchmark. A correlation analysis is conducted to compare the rankings of OI systems across different benchmarks, including Wire57, CARB, BenchIE, and BenchIE FL. The results show that BenchIE FL exhibits the highest correlation with downstream task rankings, indicating its ability to reflect real-world performance. The authors also compare the system rankings obtained from different benchmarks, observing significant differences between them. They note that recent state-of-the-art benchmarks, such as BenchIE and CARB, tend to overestimate the performance of neural models, which often produce non-informative tuples by copying large chunks of input texts. Finally, the authors conclude by highlighting the contributions of their work, including the development of new annotated resources, improved guidelines for OI annotation, and a more effective matching function. They suggest avenues for future work, including the annotation of additional sentences and the exploration of new OI approaches. This paper presents BenchIE FL, a novel framework for evaluating the performance of open information extraction (OI) systems. It is designed to address several limitations in existing benchmarks, such as lack of coverage and inconsistencies in annotations. BenchIE FL provides a comprehensive evaluation platform that assesses OI systems across multiple dimensions, including accuracy, completeness, and the ability to extract information from diverse linguistic constructions. The authors propose a new annotation scheme that categorizes extractions into correct and incorrect based on their relevance to the input sentence. They also introduce a custom matching function to measure the similarity between system outputs and gold annotations, which outperforms exact matching functions used in previous benchmarks. BenchIE FL includes a dataset of 300 sentences annotated with extractions, providing a more diverse and challenging testbed for OI systems. The evaluation results show that BenchIE FL can differentiate between state-of-the-art OI systems more effectively than existing benchmarks. The paper also discusses several limitations of BenchIE FL, including its small size and English-only availability. Future work could involve increasing the size of the dataset and extending it to other languages. Additionally, the authors suggest improving the matching function or using different features and methods to enhance its performance. In conclusion, BenchIE FL offers a robust evaluation framework for OI systems, offering insights into their strengths and weaknesses. It encourages further research in this area, particularly in terms of improving the matching function, increasing the dataset size, and expanding the benchmark to other languages. The research paper discusses the implementation details of various systems and benchmarks used for testing and comparing their performance. It highlights the use of systems like Reverb, Clause.IE, Mini, Image.IE, OpenIE 6, M2O.IE, and Compact.IE, each with its unique approach to extracting facts from text. The paper also describes the benchmarks Wire 57, CARB, and BenchIE, which are used to evaluate the system's performance. A key aspect is the introduction of alternative formulations to match extractions to annotations even when an exact match does not show correspondence. This involves the notion of rewriting pairs to authorize the removal of certain tokens for a match. The paper also compares the scoring functions of these benchmarks, showing that token-level matching has low correlation with manual rankings, while the custom matching function correlates highly with manual rankings. The research focuses on the technical aspects of these systems and benchmarks, providing detailed descriptions of their implementations and performances. The internal frame backpack, a recent innovation, was invented in 1967 by Greg Lowe. In the context of neural system scores, the experiment on the CQA task resulted in lower scores compared to the original paper's scores due to a modification in the scoring method. The original code allowed for various formulations of an entity to be regrouped in a single answer, which led to full points being awarded to answers containing multiple different elements. By separating all entities into distinct answers and computing MRR on those answers, the scoring method was made more accurate. The experiment on the KBP task involved comparing annotations from KnowledgeNet with those from BenchIE. To validate the re-annotation, objective proxies were devised to highlight differences between BenchIE's annotations and the new annotations. These proxies identified distinct clusters that might fall into one of the error categories from the experiment in section 3.1. The results showed that all proxies returned a lot more occurrences from BenchIE's annotation than from the new annotations, leading to the belief that BenchIE's annotation contains more errors. However, not all annotations matched by the proxies were necessarily errors. Examples of such annotations from both sets are presented in Table 19. In the context of the CQA task, the experiment involved re-notating the first 100 passage question pairs of web assertions, following the BenchIE format and listing all clusters that can answer the question. The results were computed using the new annotations, and the scoring method was modified to separate all entities into distinct answers and compute MRR on those answers. The system's score was closer to the original paper's scores when using the original scoring, but the new scoring method provided a more accurate evaluation. ImagIE was excluded from the experiment due to compute limitations, as it would have required more than 2 months of compute time on the setup. In the context of the KBP task, the experiment involved comparing annotations from KnowledgeNet with those from BenchIE. To validate the re-annotation, objective proxies were devised to highlight differences between BenchIE's annotations and the new annotations. These proxies identified distinct clusters that might fall into one of the error categories from the experiment in section 3.1. The results showed that all proxies returned a lot more occurrences from BenchIE's annotation than from the new annotations, leading to the belief that BenchIE's annotation contains more errors. However, not all annotations matched by the proxies were necessarily errors. Examples of such annotations from both sets are presented in Table 19. The paper discusses the evaluation of various proxies for annotating facts in text. It highlights the importance of double annotation and its significance in identifying errors. The authors verify that most cases from BenchIE are double annotation errors, whereas BenchIE FL shows a higher accuracy. The double meaning proxy is also examined, revealing a high count of errors in BenchIE. The false, irrelevant, missing facts proxy shows an inversion in counts, indicating that the author's annotation is more exhaustive. The paper provides detailed examples from tables 18, 20, and 21 to support these claims. It emphasizes the need for a more comprehensive annotation approach, incorporating inference and adhering to the minimality principle. The author's annotation is shown to be more accurate, with fewer irrelevant formulations of facts. The paper concludes by highlighting the significance of accurate fact annotation for better understanding and utilization of text data. Here is a combined summary of pages 17 and 18. The presented research focuses on the evaluation of various information extraction systems, including Reverb, Clause.IE, Mini, Emoji, OpenIE 6, M2OIE, and Compact.IE. These systems are tasked with extracting relevant information from natural language sentences. The extraction examples in Table 20 demonstrate the performance of each system on a specific sentence about John Crozier, Jr., an early aviation pioneer. The systems identify relationships between entities, such as his son and John Crozier, Jr., and extract relevant information, including the fact that John Crozier, Jr. began building a human-powered flying machine in the 1890s. On page 18, the authors present BenchIE and BenchIE FL, two annotation systems for evaluating information extraction performance. The systems annotate sentences with relevant information, such as entity relationships and event extractions. The annotation examples in Table 21 demonstrate the performance of BenchIE and BenchIE FL on a sentence about the release of My Classical Way on September 21, 2010, on Mark's own label, Frazzy Frog Music. The annotation clusters in Table 21 show the various ways in which the annotation systems extract information from the sentence, including the release date, label, and ownership relationships. For instance, Cluster 1 extracts the release date and event information, while Cluster 2 extracts the label and ownership relationships. Overall, the research presents a comprehensive evaluation of information extraction systems and annotation tools, highlighting their strengths and weaknesses in extracting relevant information from natural language sentences. The annotation guidelines presented in this appendix dictate which facts should and should not be annotated for the open information extraction task. The principles include the number of arguments, informativeness, minimality, exhaustivity, relation completeness, and CO reference resolution. For instance, tuples must contain between 1 and 2 arguments, be informative and relevant, and contain minimal information that cannot be subdivided. The guidelines emphasize the importance of exhaustivity, ensuring all minimal information present in the sentence is included, and relation completeness, where relations are simplified as much as possible without losing their original meaning. Coreference resolution is performed outside sentences, focusing on isolated sentences for the task. These principles are demonstrated through examples, showcasing how sentences should be annotated, including those that should not be included, to ensure the quality and relevance of the extracted information. Here is a combined summary of pages 21 and 22. The concept of inference is essential in open information extraction, OI, where facts directly implied by a sentence are considered relevant pieces of information. However, a nuance is necessary to distinguish between light and heavy inference. Light inference refers to a form of inference that does not require logical reflection, whereas heavy inference requires some reflection or combination of logical operations to imply the fact, often involving external knowledge or generalization. The paper provides examples to illustrate the distinction between light and heavy inference. For instance, in the sentence, Paul Johansson, Monsanto's director of plant sciences, said the company's chemical spray overcomes these problems and is gentle on the female organ. The fact that Paul Johansson is Monsanto's director of science is a light inference, whereas the fact that the company's chemical spray is gentle on the female organ is a heavy inference requiring external knowledge. The paper also discusses reformulation, where a simpler reformulation of the same fact is added to the same cluster, even if the relation in the two formulations is not the same and the level of detail may be different. This is a compromise between the goal of collecting all the factual information expressed in the text and the importance of formulating these facts in simple language. Furthermore, the paper addresses active and passive voice, where clusters are used to group together the active and passive formulations of an extraction in a single fact. It also discusses attribution and speculation, where information in the text is speculative or attributed to an entity, and this characteristic must be included in the relationship. Additionally, the paper touches on correction, where tuples may consist of words from the original sentence but contain grammatical errors, and both the original and corrected tuples should be included in the same cluster. Finally, the paper outlines the matching guidelines for the open information extraction task, including principles for exact match, relation specificity, and other aspects of matching extractions made by systems and annotations. The Finns party was thrown out of the government, and the new, Blue Reform Group kept its cabinet seat. In terms of relation specificity, some system extractions may present syntax or grammatical errors, such as misplaced or unnecessary words. If these errors change the meaning of the relation or one of the arguments, the extraction should not be matched. However, if they do not alter the meaning, the extraction should match the corresponding annotation. In another context, known for his albums of classical piano compositions, he is also a producer and songwriter. The word choice in system extractions can vary from the reference annotations in certain contexts, but if the meaning remains, the extraction is still accepted. For instance, using the determiner, the, instead of a, in the extraction is acceptable since both are appropriate. He is the younger brother of the prolific film composer Christoph Beck. Regarding the level of detail, we want to match extractions that have a higher level of detail than the annotation but convey the same information. If an extraction combines information from two annotated clusters, it is considered useful. However, if it combines information from 3 or more annotated clusters, it is considered too noisy and imprecise. An example of a positive match would be an extraction that conveys the same information as the second annotated cluster and adds a single level of detail from the third cluster. Conversely, an extraction combining information from all 3 annotated tuples into a long and imprecise second argument is not matched. Alex broadcasts a web series music on a website. The extraction is matched because it conveys the same information as the second annotated cluster and only adds a single level of detail from the third cluster. An extraction combining information from all 3 annotated tuples into a long and imprecise second argument is not matched.